Okay, hello everyone. I welcomes to all in our lecture series on optics belongs to B.sc Physics on our syllabus second semester core paper 4. In this video we are going to discuss second part of your Fresnel's diffraction. In our first part video we have been discussed introduction about diffraction, Fresnel's assumptions, Fresnel's half period zone. These topics already we have been discussed in our first part video. Okay, in this second part we are going to discuss Coronal spiral or Euler spiral and Fresnel's integrals. Okay, so let's start. So in our first part we are already discussed these three topics, and in our second part in this video we are going to discuss this one and this one, Coronal spiral and or Euler spiral and Fresnel's integral. So may you remember that these things already we have been discussed in our first part about introduction about your diffraction. This is your diffraction pattern. This is this area and this area will be called as the shadow region. These things already we have been discussed. If this slit width will be few nanometer range, then diffraction pattern will be observed. That we are already discussed. Then we have been discussed about Huygens wave theory. According to this wave theory, we have been concluded that from a primary source, wave fronts are propagating in all the directions. In all the directions, wave fronts. This is the wave front. This is the wave front. So wave fronts is going to be propagating in all the directions, and different types of wave fronts also we have been discussed. And here we discussed that how the diffraction pattern will be observed by considering two situations. Here is the slit and here is a opaque object. If you are going to consider by considering this Huygens wave theory, we can get diffraction pattern. Okay, these things also we have been discussed in our last video. And here in our last video also we have been discussed one of the important topic, that is your obliquity factor, that is your 1 plus cos theta. Obliquity factor is your 1 plus cos theta, that we have been discussed in our last class. Here I am going to discuss in shortly about obliquity factor. So here you can see that suppose we intend to find out the effect or intensity at this point due to this first half period zone, and intensity at point P due to this first half period zone, and what will be the intensity at point T due to the first half period zone. See, this is your first half period zone, and this is your second half period zone, this is your third half period zone, this is your fourth, like this. So due to first half period zone, what will be the effect at O? First we have to calculate. Here obliquity factor is nothing but 1 plus cos theta. So we intend to find out the intensity or effect at O. So when the light passed through the first half period zone, it moves straight to the O. Okay. So here theta will be how much? Theta will be equal to 0. Theta will be equal to 0. So theta will be 0 means cos theta will be how much? 1. So obliquity factor we found equal to how much? 2. So effect or the so-called intensity will be maximum along CO path. Now consider a arbitrary point P on the screen, and we intend to find out the effect at point P due to the first half period zone. So from the first half period zone, if we want to move towards the point P, then we have to create some angle from the horizontal direction. From the horizontal direction, we have to create some angle theta. So here theta is the angle we have to create from the horizontal, then we can reach at the point P. Okay. So if this theta will be 45 degrees, suppose if this theta will be 45 degree, then 1 plus cos theta, 1 plus cos 45, that will be 1 plus cos 45, 1 by root 2. So this will 1.1 by root 2 is around 0.7. So it will be 1.7. So initially it was for obliquity factor for at the point O due to the first half period zone we found how much? 2. But at point P due to first half period zone it is reduced 1.7. From 2 it is reduced 1.7. So here obliquity factor is reduced whenever we are going to move away from the horizontal. Now we are going to consider another point T from the horizontal. Let we have to move the angle pi by 2. So from the first half period zone, if light will be travel to T, let it has to create pi by 2 angle with horizontal. So if pi by 2, here you can see pi by 2 means cos pi by 2 will be 0. So obliquity factor will be 1. So here obliquity factor how much is reduced continuously whenever we are going to go away from the horizontal. Okay, so here obliquity factor decreases, so hence intensity at the point T due to first half period zone is going to be reduced. Okay, so here we found that as obliquity factor decreases, then the intensity at the arbitrary point is going to be decreased. So if we have to move from horizontal to this way on the screen, then the obliquity factor, this one, is decreases, due to which the intensity that on at that particular points is going to be decreases. Okay, intensity also decreases. So along CO the intensity is maximum, along CT it is the intensity is to be decreased. Okay, now we are going to consider another angle. Suppose we are going to consider theta equal to 180 degree. Theta equal to 180 degree means we are considering that the wavefront is traveling along this direction, along backward direction. See, this is the wavefront means this is a circular wavefront. This is also circular wavefront. From this source, wavefront will be traveling in all the directions. But here we are measuring the intensity right side of the slit. If this is your slit, we are measuring the intensity right side of the slit, or screen is present right side of the slit. Okay, right side to the slit. So that as screen is present right side of the slit, so wavefront which are moving in this direction, that will be considered. The wavefront which are going to be moved backward direction, that wavefront not to be fall on this screen. So these wavefronts not to be considered. Suppose this wavefront can be moved in all the direction backward also, but where is the screen? Screen is this right side. So the wavefronts which are moving backward not to be considered. Okay, not to be considered. So only for that, for theta, when theta is 180 degree, means if theta is 180 degree, that means this is 180 degree, this is the 180 degree theta. That means it is telling that we have to consider the wavefront which is moving backward. But here backward we not have any screen. We have the screen in the right hand side. So whatever the wavefront moving backward not to be considered. Same thing it has been written. Obliquity factor will be 0. It is suggested that secondary wavefront eliminated or not to be considered. Okay. Also, we discussed in our last video how to obtain the half period zones. In detail, these things already we have been discussed in our last videos. We have to construct the imaginary circles by considering O is the center. Blah blah. Already we have been discussed in our last class in detail. For this is the spherical wavefront. Okay. Similarly, for the plane wavefront, also we discussed how to construct the Fresnel's half period zone. Then we have been considered then we have been discussed about Fresnel half period zone and radius of Fresnel's half period zone. Here you can see this is the center, and up to end of this zone, this is so called the radius of the first half period zone. End of this zone is your second half period zone, radius of the second half period zone. And here we consider this point is belongs to M3. So from this point to this point is your radius of third half period zone, and so on. Already we have been discussed. And here one thing you have to remember always, that you should not be think that light only passed through this white zone. No, light will pass through this white zone as well as this dark zone. See, for the representation of the alternative zones, here it is represented by white, black, or white, dark, white, you can say black zones. But light will pass through this zone, first half period zone, and light also passed through the second half period zone. But what is the condition, whatever we are going to discuss in our last class? From first half period zone to second half period zone, the phase difference is pi. So if the light is passed through the first half period zone, and if I am going to compare the light which is passed through second half period zone, both have the phase difference is your pi. So if we want to find out what will the path difference, if phase difference between the two zones, first and second zone, is your pi, then the light coming from first zone to P and light coming from second zone to P, what will be the path difference? It will be lambda by 2. Already we haven't discussed, because phase difference equal to 2 pi by lambda into path difference. So if phase difference will be pi, then path difference will be lambda by 2. That also we have been discussed in our last class. And here you can see that if, see, from the first half period zone, whatever the light coming and falling at point P, and corresponding the second half period zone, whatever the light coming from the second half period zone and falling at point P, both have phase difference is pi. Phase difference pi means, suppose from the first half period zone, whatever the light coming coming and falling at point P, its amplitude is m1, and the vibration due to first half period zone, whatever the light passing through the first half period zone and its corresponding vibration at point P, if along this direction, due to second half period zone, it will be reverse direction, because the angle is, the phase difference is pi. So the vibration, if due to first half period zone, will be in this direction, for the second half period zone will be this one. And if the first half period zone amplitude will be m1, this much, then second half period zone will be this much. It will be somewhat lesser than the first half period zone, and it will be reversed to the first half period zone. For third one, again it will be pi phase difference according as compared with the second one, so it will be reversed with second along this direction, and again it is reduced to its amplitude. Likewise, from fourth half period zone, this one, the amplitude will be called as m4, and its vibration will be opposite to the third one. Like that, it will be considered for the, it will be considered for next to next half period zone, and its a corresponding amplitude of vibrations at point P. And at point P, what is the resultant amplitude? So this is the amplitude and direction of due to the first half period zone. This is the amplitude and direction of vibration due to second half period zone. This is the amplitude and direction due to third half period zone at where? At the point P. So resultant amplitude at point P will be how much? M1 plus M2, but as M2 is your reverse direction as compared with M1, so it will be written as, it will be minus M2, and M3 along same direction with M1, so it will be plus M3, then minus M4 plus M5, and so on. These things already we have been also discussed. Okay. So here up to this much we have been discussed in our first part video, and in our second part, this part we are going to start Coronal spiral or Euler spiral. Okay, carefully you have to watch this one, right? Here you can see that to understand the Coronal spiral or Euler spiral, here you can see that this is our alternative half period zones. This is your first half period zone, this one, this dark one is your second, this one third, fourth, fifth, sixth. These are the alternative bright and dark strips or zones, whatever we have been discussed in our last class, right? Now to obtain or to represent graphically the intensity distributions or the so-called Coronal spiral, here what we have to consider, or the Fresnel considered that first half period zone, this one is the first half period zone, this one is your first half period zone, fast half period zone divided into 8 substrips. 8 substrips. It can be any substrips, any number of substrips. To understand here we consider that, let consider fast half period zone divided into 8 substrips like this. So here 1, 2, 3, 4, 5, 6, 7, 8. 8 substrips. So this half period zone again subdivided into the 8 strips. Okay, 8 strips. These vectors are represented from O to M1. The continuous phase changes due to the continuous increase of obliquity factor from O to M1. The resultant amplitude of vibration at point P to fast half period zone will be OM1. What are the written over here? You just write down in your note. We are going to discuss one by one line. Okay. So here we consider that fast half period zone again subdivided into 8 substrips. Okay. So here you can see that this is your fast half period zone. Okay, this is your fast half period zone, and this is the light source. From this light source, light is travels through the fast half period zone. When it will pass through the center of the fast half period zone, it will falls on O. Okay, falls on O. Okay. And as we discussed that due to the obliquity factor, if we want to find out the intensity at point P and T, then the angle will be increases due to the increase of angle. We know that the obliquity factor will be 1 plus cos theta, then theta will be increases, means this value will be decreases, the obliquity factor will be decreases. These things already we have been discussed. And also we have been discussed in our previous slide that M1 is the amplitude of vibration at point, suppose at point O due to the fast half period zone. M2 will be the vibration at point O due to the second half period zone, which is the phase difference pi as compared with M1. Okay, these things already we have been discussed. Now here we found that whenever the obliquity factor is going to be decreases, the corresponding intensity will be decreases at a particular point due to the different zones. Okay. Now here the fast half period zone is divided into 8 strips. So here you can see that from this center, if we have to move up to edge of this half period zone, then also obliquity factor is going to be changed, and the net intensity or the net amplitude for this half period zone, whatever we have been considered M1, then this M1 will be equal to addition of some amplitudes whenever we have to move from this point to edge of this half period zone, edge of this fast half period zone. Okay, see here in detail you can understand. This is your fast half period zone, which is subdivided into 8 strips. Okay. So as we discussed that if we are going to move from horizontal towards this direction, then the obliquity factor is going to be decreases. If obliquity factor is going to decreases, the intensity also going to be decreases. Okay. So same thing is going to happen. Here we are going to consider the obliquity factor and corresponding intensity of the fast half period zone by each and every strips from center to edge of this fast half period zone. Here from the center to edge of this fast half period zone, the point is nothing but your M1. Okay. Okay. See here clearly you can understand. This is your center of the fast half period zone, which is again subdivided into 8 strips, right? So if the light will be moved from this strip, then it will fall at O. Okay. Okay. Now consider the second strip, this one. this one, whenever the light will be passed through this second strip, suppose from this point we are going to consider, then the light will be moved along this direction, having greater amplitude will be fall on the screen over here. But if we are going to consider from this point, if the light will be travel along this direction, along O direction, means from this point to O, from this point to O, then it has to bend in an angle theta. Okay, an angle theta. So then here obliquity factor will be come into the picture. For this second strip, again I am going to repeat. See, for the second strip, if the light will pass from, it will be starts from here, then it will be move straight and fall over here with higher intensity. But if we are going to consider the part of the light will be bent towards the O, then it has to bend theta angle. So if theta angle means the obliquity factor will be 1 plus cos theta. So whatever the intensity we can found in straight, if it will be bent, then the intensity is going to be decreased, because obliquity factor is going to be decreased whenever theta is going to be increased. So if theta increases, this intensity, this ray intensity is going to be decreased. Okay, likewise you can consider this one, this half period, this strip. From this strip, light can be straightly move onto the screen over here, but we intend to find out the net intensity at point O. So for that, if we want the light, the light will be bent towards the O, then it will be bent with a larger angle as compared with this one. Okay, with a larger angle as compared with this one, with larger angle as compared to this one, this angle. So larger angle, suppose this one theta 1. So the obliquity factor will be 1 plus cos theta 1. So here 1 plus cos theta, suppose here 30 degree, this will be 60 degree. So as this will be 60 degree, theta 1 will be 60 degree. So obliquity factor will be decreased. If obliquity factor will be decreased, so as we are going to move from center to the edge of the first half period zone, then the intensity at point O due to each strip will be add up. Okay, so due to first half period zone, due to first strip, if the intensity or the amplitude at point O is your A, for the second strip, whenever the light is going to be bent to O, angle theta, then the amplitude will be B at point O. Okay, and it will be decreased as compared with A. If A amplitude is this much, B amplitude will be reduced. Okay, then as we have to move from this center of the first half period zone to the end or the edge of the first half period zone or up to M1, then here we considered 8 strips. So we have to add the amplitudes of 8 strips, 1, 2, 3, 4, 5, 6, 7, 8. So M1, which is already considered that the amplitude due to the first half period zone will be written as the amplitudes of 8 strips, whatever we have been considered here. Okay, here is the 8 strips. So due to 8 strips and corresponding their obliquity factor, the intensity or the amplitudes is going to be added up, A, B, C, D, and the resultant will be M1. Okay, this is the discussion about first half period zone by considering 8 strips for the first half period zone. Similarly, the second half period zone, this one, can be considered strips, some number of strips, and due to this strip, what will be the net intensity or net amplitude? This is your M2, and as we consider that the second half period zone is to subdivided into large number of strips, large number of strips. Suppose we consider the 5 strips. Second half period zone is subdivided into 5 strips. 5 strips. Okay. Hence M2, which is the amplitude at point O due to second half period zone, will be written as likewise A B C D F G H I plus J plus K I J K plus L plus M. So I is the in amplitude due to the first strip of the second half period zone. J is the amplitude at point due to second strip of second half period zone. K is your amplitude at O due to the third strip of the second half period zone. Likewise, A is the amplitude at O due to the fifth strip of the second half period zone. So likewise, we can consider for the third one, fourth one, and so on. Okay. 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 So whatever we have been discussed over here, now we are going to draw all the vectors. See here, A is one vector, B is one vector, C is one vector having decrease of amplitudes and changes corresponding phase angles. Or you can see from the second half period zone, if this is the theta, from the third half period zone the angle will be this one. The angle will be here. For the third half period zone, it will move to straight. The angle will be this one. For 7th, suppose last one. For 8th one, the angle will be how much? The angle will be this one. So as we have to move from the first strip to 8th strip, gradually the angle increases. Or we can say the phase also increases. Okay, phase also increases, or phase difference we can found. So these vectors now we are going to draw in a graph in a xy plane. How? Here we have to move for the second slide. Here these things already we have been discussed. Here you can see that first half period zone divided into 8 soft strips, and these vectors. Okay, here you just try to understand soft strips and how the amplitudes of each and every strips up to 8th is going to be changed. That already we have been discussed, right? Now we are going to draw these amplitudes in the xy plane. Okay, so this is your x axis and y axis. This is your x and y axis. Okay, the first vector is represents the amplitude of vibration due to the first strip. Okay, first strip due to this strip at the point O on the screen, at the point on O on the screen here. Okay, okay. So this is the vector having direction and amplitude of the light which is passed through this first strip, right? Now B vector having somewhat decreased of magnitude passed through the second strip and falls on the screen, and C is the vector having direction and magnitude D, E, F, G and H. So here the 8 strips are there. So due to the 8 strips, as we discussed in our previous slide, that due to these 8 strips we can get the we can get the variation of amplitudes on the screen at a particular point. So these 8 vibrations or amplitudes are represented in your xy plane. So M1 is nothing but the end of the first half period zone, or the 8th strip. Due to the 8th strip, this is the point belongs to M1, remember it. Okay, and M2 is this point at the edge. Okay, so this is your M1 This is your M1. And if I'm going to here you have may you are going to remember in our last class also we have been discussed that the age, this age is your M1, this is your M2, this is your M3, this is your M4. Likewise we are going to get nth. For nth it will be n minus 1 lambda by 2. Already we have been discussed. Okay, so now here this vector is the resultant vector. If I will be close, we know that the vector addition of a polygon, so this will be the resultant vector of this polygon. The value is your m1, and this m1 is nothing but called as your amplitude of vibration due to first half period zone. Likewise, for second half period zone, if we are going to consider the large number of strips, here we consider 1, 2, 3, 4, 5. 5 strips, suppose. 5 strips. Second half period zone is considered as 5 strips. Okay, so from M1 to M2, so M2 is represents the end of the second half period zone. Okay, so here is the 5 strips and the intensity distribution due to each strip are this one for first, second, third, fourth, fifth, and the end will be end one, which is nothing but your M2. Okay, the end one is your M2. This one will be M2, and due to this vector addition, the resultant of these vectors will be this one, and this one is nothing but M2. Is your amplitude of vibration due to first half period zone. This one is your amplitude of vibration due to second half period zone. So resultant will be how much? Resultant will be A. Okay, here A is nothing but equal to how much? Here you can see M1 minus M2. M1 minus M2, because M1 is the amplitude of vibration due to first half period zone along this direction. Okay, and M2 is the amplitude of vibration due to second half period zone along this direction. So obviously the resultant A will be M1 minus M2. Now we are going to consider that suppose we here this first, second completed. Okay, suppose third half period zone we are going to consider third half period zone. Again, third half period zone, suppose it is subdivided into number of strips. These strips are circular. Okay, circular strips. Then here you can see that here third half period zone 1, 2, 3, 4, 5. 5 substrips also here we considered are as per the example only. So you can consider any number of strips. So here 1, 2, 3, 4, 5. So for first strip it will be this one, and for the second strip it will be this vector, and this vector at exactly at the end of the third half period zone, which is nothing but M3. This point is your M3. So obviously this point will be M3, right? This point will be M3, and likewise we can consider its resultant. Resultant vector will be this one. We can consider resultant vector will be this one due to only considering the third half period zone. Okay, third half period zone. So due to third half period zone, this one will be M3. Okay, next if we are going to consider fourth half period zone, and it is subdivided into 1, 2, 3, fourth half period zone is subdivided into number of strips. So this end will be your M4. So this will be your M4. This end will be M4, and this is the close end, and this is not, this value will be nothing but how much? M small m4. This magnitude will be M4. So if we are going to consider first, second, third and fourth half period zones, then what will the resultant amplitude at point O, on the screen? That will be M1. This one is your M1. This one is your M2. This one is your This one is your M1, this one is your M2, this one is your M3, and this one is your M4. Here you can see that M1 along this direction, M2 approximately it is opposite to this one, so it will be subtracted. So M1 is going to be subtracted from M1, sorry, M2 is going to be subtracted from M1. Then M3, here you can see M3 along this direction, so it will be add up M4, this one M4, this one M4, this direction M4, it will be subtracted. Okay, so this way we found a spiral like a geometry or structure whenever we are going to go through the intensity of distribution or amplitude of vibration at a particular point on the screen due to each and every zones by considering the number of strips as per the Fresnel. Fresnel assumed that the each and every Happiness zone further divided into strips. Okay, so whenever we considered or whenever we drawn these amplitudes for each and every zone, for first Happiness zone, this will be up to this much, up to M1. For second Happiness zone, up to M2. For third Happiness zone, from here to M3, capital M3. Okay, for fourth Happiness zone, this will be up to M5. For fifth Happiness zone, it will be up to this much. For sixth Happiness zone, it will be up to this much. Like this, Fresnel has been got. So this spiral-like structure, whatever represented mathematically, this of all the amplitude of distribution of all the Happiness zones by considering strips, okay, is called as your Coronus spiral or Euler spiral. Okay, Coronus spiral or Euler spiral. So same thing it has been written that these vectors are represented from O to M, that is from O to M. For first Happiness zone it is written. Then the continuous phase changes due to the continuous increase of obliquity factor as we have discussed. See, this is along this direction, tangentially this is along this direction. So obviously the phase will be changed as direction changed from one vector to another. Then obviously its phase is going to be continuously changed. Okay, as obliquity factor from O to M1, O to M1, here O to M1 obliquity factor, O to M1 obliquity factor changed, so corresponding phase also changed from O to M1, right? The resultant amplitude of vibration at point P due to the first Happiness zone will be OM1 or M1. OM1 will be M1. Here we have to just modify this one, that see, here we are trying to find out the intensity distribution at point O on the screen due to all the Happiness zones. So the resultant amplitude of vibration at point O on the screen due to the first Happiness zone will be OM1, from O to M1. Okay, these things already we have been discussed. Sorry, OM1, this one, OM1, that is the value is your small m1, right? Likewise, similarly, if we consider second Happiness zone, we obtain the vibration core from M1 to M2. From M1 to M2, this core, this is the resultant core due to the second Happiness zone, and the amplitude is will be M2. Okay, that is from M1 to M2. This vector for the second Happiness zone. So vibration at point P due to the second Happiness zone will be M1 M2 or small m2. Hence, the resultant amplitude of vibration at point O due to first and second half period zone will be how much? O to M2, that is your A, already you have been discussed. Okay, you just write down the note here. Okay, so this will be OM2, that is your A. Okay, if half period zones are to be considered as substrips of infinitesimal width, then we can get the smooth curve. See, this is the curve we found the addition of E for each and every strips for the first half period zone. This curve from here to here we found for the second, this curve for the third, this curve for the fourth half period zones. So if we are going to see, here we consider the first half period zone belongs to 8 strips. If we are going to consider 100 strips, then the vectors will be very close with each other, and we are going to get the smooth curve. Okay, so same thing it has been written that if we are going to consider the substrips of infinitesimal width, then we can get the smooth curve. Now, if we have considered all the half period zones, the complete vibration curve will be a spiral. Now, here we considered only first, second, third, and fourth half period zone, and we found a spiral-like structure or curve of amplitude of distribution at a particular point on the screen. This is the representation mathematical representation or vectorial representation in a 2D plane, and we found a spiral like structure by considering only 4 half period zones. Okay, if we are going to consider all the half period zones, that means next 5, 6, 7, 8, then this will be like this, okay, this will be like this. So this will be like a spiral, which is called as your Coronal spiral or Euler spiral. And here you can see the resultant amplitude will be how much? A will be how much? Your M1 minus M2. M1 minus M2 by considering first and second half period zone. If we are going to consider third half period zone, for the third half period zone the vector will be this one, so it will be plus M3. For the fourth half period zone it will be this way, minus M4. Likewise for fifth, again it will be plus M5. For sixth, minus M6, and so on. Right? So this is your so-called Coronal spiral, formation of Coronal spiral. Okay. Here another important thing we have to remember. What is that? Here you can see whatever the spiral we found here by considering the upper half of the zone. See, from this point to this upper half, the first half period zone, what is the curve we found from O to M1, right? From O to M1, this curve is nothing but by considering only upper half of the first half period zone. Like similarly for the upper half of the second half period zone, we found this curve. By considering upper half of the third half period zone, we consider this curve. Okay, by considering upper half of the fourth half period zone, we found this one. But half period zone, if we are going to consider this one is your first half period zone, upper half is there, lower half is also there, lower half. Okay, for the upper half, this curve we found. Likewise for lower half, for the first half period zone, also we can get this one. Okay, if this one is your M1, here we can get M1 prime, right? Now for upper half of the second half period zone, we have to find from M1 to M2. So here like this we can find M1 prime to M2 prime, then M2 prime to M3 prime. Okay, like this. Okay, here M1 prime, then M2 prime, M1 prime, then this will be M2 prime. Okay, M2 prime, then this will be M3 prime, this will be M4 prime. So this entire this entire spiral curve in this quadrant and in this quadrant. This is the first quadrant it will be formed, and it will be formed at in your third quadrant. So first quadrant and third quadrant along with this will be called as your Cornus spiral, right? This is entire. This is called the Cornus spiral. So ideally it will looks like this one. So this is your Cornus spiral. Okay. Now if we have to consider all half period zones, the complete vibrational curve will be a spiral like this. So this is a ideal spiral. Whatever we have been drawn by considering 8 strips for the first half period zone and 5 strips for the second half period zone. This is not looks like continuous, but if we are going to consider the each and every half period zone will be the smooth strips, then we are going to get this type of curve, which is appeared in the first quadrant and third quadrant also. Here you can see that this one starts from O. For the first half period zone we found M1, here M1, here M1. From here to here to here, this is your M2, M2. From here to here, this point is your belongs to M3, M3. Okay, from here to here M4, then here to here M5, and the center of this spiral, center here we considered S in the first quadrant. It's just mirror image we can found in your third quadrant. In third quadrant, see here M1 means this will be M1 dash, this will be M1 dash. Here you can see that M3, so this will be obviously M3 dash. Okay, next M5, M5 dash. So here you can see this will be M1 dash and opposite will your M2 dash. Here M1 we found and just opposite here M2 we found. Okay, here just the mirror image we found in your third quadrant. So entire this curve is called as your Cornus spiral or Euler's spiral. Okay. Same thing it has been written, no problem. So characteristics of Cornus or Euler spiral. So here characteristics of curve is that for any point P on the curve. Now we are going to consider any point P. Suppose this is the point P on the curve. The phase angle, that means if we are going to consider this point is P, and if we are going to draw a tangent through the point P to this x-axis, then this angle will be called as your phase angle. So here phase angle is directly proportional to the square of the distance, and distance here this is small v, here it is written as small v. See distance, why I am written, because many books have written this symbol small v. You can write small s, no problem, but I suggest that you just write, for this case the distance is your small v. So here delta, this delta phase angle is directly proportional to the square of this distance. What is this distance? This distance is nothing but, here you can see, this is the distance measured along the length of the curve from O to P. From O to P, this distance, this is the point P. From O to P, this distance is nothing but small v. Okay, small v. And here delta is directly proportional to the v square. How it will be, that we are going to discuss in our next class. So here you just again watch that if we are going to consider this one any point P on the curve, and we are going to draw a tangent through that point, and it will be touches to the x-axis, and the angle is nothing but called as the phase angle. And here you can see, if we are going to consider this point and I am going to draw the angle, this is called as the delta. Okay, here this is called as the delta, and this delta will be the so-called phase angle, called as the phase angle, and directly proportional with the distance from this point, from the O to that point, this distance. Okay, how it will be directly proportional to this distance? Okay, that we are going to discuss in our next class. Okay, and next class also we are going to discuss Fresnel's integral in our next class. Next class means in our the video number part 3 video we are going to discuss his Fresnel's integral. Here in this class we discussed Cornus integral or Euler integral, how it will be formed, that we have been discussed in detail. In our next class we are going to discuss Fresnel's integral, because to discuss the Fresnel's integral, this is important, how this value, this length or this phase angle is proportional to v square. This is required to derive the Fresnel's integral. This relation is required. Okay, so in our next class we are going to discuss these things. Okay, so thank you so much for watching this video. Thank you.